Welcome back. Today we review the refined design pattern for generative AI applications. This video follows a recent video I've made on the channel about the MapReduce design pattern. Those design patterns are pretty useful when you are dealing with documents that are too big for the context size of your large language model. In this video, I will first go through the theoretical explanation and then through the practical implementation using Python from scratch. Let's go. Designing generative AI applications typically involves feeding information to an LLM at some point to get some output in a given shape that makes sense for your application. This shape can be textual or structured. However, doing so you will encounter a hard limitation, which is the context size of your large language model. Indeed, your model can process infinite quantity of information. And even though modern models tend to have bigger and bigger context size, we typically see that their ability to recall specific information drops. So, we need a way to divide and conquer this problem, to break down our big document into smaller chunks that we can process with our LLM to achieve our goal with good performance, and refine its design pattern to exactly achieve that. Throughout this video, I'll reuse the example of summarizing a document. So you have a big document, and you have a query, summarize the document. To do so, you have an LLM. But we encounter the limitation, the document is too big for the context size of our model. At this point, you need to ask an important question. Is the information in the document dense or sparse relative to the query? If the information in the document is dense relative to the query, it means that you have to process the entire document to produce the final answer. Summarizing a document falls into this category because you don't want to miss any important information when you produce the final summary. If the information in the document is sparse relative to the query, it means that only specific parts of the document are relevant to the final output. And in this case, we'd rather find those specific important parts and use them to produce the final answer. An example would be, what is the name of the main character in a book? Typically, it would require only reading the few first chapters to answer, and would like to only use this information to produce the final answer and avoid all the noise of the entire document. The refined design pattern that we'll review today is helpful in the first scenario, when the information in the document is dense relative to the query, and so when we need to process the entire document. Here is how refine works. The first step is to split our big document into smaller chunks. The important part here is that each chunk should be smaller than the maximum context size of our LLM because we need to be able to process each one with the model. The next step is to write two prompts. The first prompt is used to produce the first answer. It takes as parameter the query, so summarizing the document here, and the first chunk. It will produce a first incomplete answer that will be refined with the second prompt. The second prompt uses the query, the current answer, and the current chunk to produce a refined answer. So it takes the first answer, or the previous answer, and make it better with the current chunk. And we do it in a recursion. So we call the second prompt with all subsequent chunks to get the final answer. Here is how the recursion unrolls. We use the first chunk here with the first prompt and we get the first answer. Next, we use the second chunk here together with the first answer and the second prompt to produce the first refinement. And we do so for the third refinement, the fourth refinement, fifth refinement, and the final answer. So if we summarize, there is three main steps. First, the chunking, we break the document into smaller pieces, then producing the first answer, and then playing the recursion to get the final answer using the second prompt. Now, it's important to review the trade-off of this approach. First of all, it helps you overcome context limitation with your LLM, and also performance limitation, when you have a big context, but the performance of the LLM is not that good on big documents. It can also process documents of any length, and it maintains context across the entire document. However, it's computationally intensive for very long documents, because on the contrary of the MapReduce, where you can parallelize the map step, with refine and the recursion, you need to process every chunk one after the other, so it can take a lot of time. Also, it can introduce a bias towards earlier chunks of information. Indeed, the model might generate a first answer and then be wary of integrating new information to the answer. It's a problem I encountered sometimes with this technique. Now, for the use cases, you have document summarization, comprehensive question answering, content analysis of long reports, extracting insights from a research paper, and so on. Every time you need to process a document in a dense way, so meaning you need to process the entire document to produce the final answer, refine can be an interesting choice. And finally, it's time to put the theory in practice. So, we import a few libraries to start. First, .env to load the environment variables that contains the API key of our LLM. LightLM, which is a module that helps you run any models easily, whether it's OpenAI, Sonnet, or something else. And finally, the Wikipedia package to load a web page and try to summarize it. It will be the purpose of this demo, try to summarize a wiki page. Second step, we define some generic parameters. Here we have the chunk size, we define 15,000 characters. It's just for the purpose of the demo, there is no specific meaning behind this number. And the query, summarize the concept of transformers. We first get the content from Wikipedia. To do so, we download the transformer page that contains the text of the transformer deep learning architecture. Then we define a chunker function that takes a sequence and a size and returns a sequence of chunks. The next step is to define the two prompts. So the first prompt, the init prompt, takes the question and the text, so the first chunk here, to produce the first answer. And then we have the refine prompt that takes the question, the previous answer, and the new text, which is the current chunk here. Now, we start answering the query. To do so, we split the document into the manageable chunks, and then we init the first answer. To do so, we create the prompt, we stack the message, and we call the completion using Claude 3.5 Sonnet. Then we get the correct answer, we print it. So as you can see here, we get 7 points, 8 points, so it's the point extracted from the first answer. This answer is incomplete because we only saw the first chunk. Then we go to the refine loop. So here in the loop, we will refine using the second prompt. To do so, we define the prompt, we also stack the messages, we create the response with the completion, and then we update the current answer. So every time the answer gets updated, and we reuse the current answer at the beginning of each loop step. And finally, we print the final answer and we get a more complete summary. So here, as you can see, it covers 19 points. So the application, multimodality, and so on that we didn't see in the first answer, showing that the refinement works and helps you extract the entire summary from a big wiki page. If you need to process a document that is too big for the context size of your LLM, first ask the question whether the information in the document is sparse or dense relative to the query. If the information in the document is dense, then you can use multiple techniques, and refine is one of them. If you like this video, you can check out the video about the MapReduce design pattern. See you in the next one.